Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So today we will be looking at a problem called longest increasing subsequence. So in the last couple of lectures we have seen some problems and how to solve them, mostly using dynamic programming. This is one such problem also. Let's start with it. The idea is that given a sequence of integers, we want to determine the longest increasing subsequence, or in other words, a subsequence is simply a set of elements in the sequence. That is, we take the original sequence, we can drop some of the symbols there, and whatever we left with is this a subsequence. If the elements of the subsequence is increasing, that means if a particular symbol is picked up and it is smaller than all the other symbols that are picked up after it, then it is called an increasing subsequence. So, we want to look at a longest increasing subsequence. So, let us start with an example. So, here say is a list of or a sequence of integers. Now, these integers are not sorted or any such things. Now, what is the longest increasing subsequence? First of all, what is an increasing subsequence? So, an increasing subsequence is anything like it says start with 8, 9, 9, 10. So, this is an increasing subsequence because I have picked up elements from this sequence and it is increasing 8, 9, 9, 10. Similarly, I can have some more things, for example, say 2, 5, 7, 9 and 10. This can also be an increasing subsequence. Note that the earlier one had a length of 4, that means I had picked up 4 symbols. So, the subsequence length was 4. In this case, I have picked up 5 symbols and the subsequence length is 5. So, the goal is to find the longest increasing subsequence. Say in this case, the longest increasing subsequence is quite long. It is actually this 8 sequence. So, let us try to see it 2, 5, 7, 7, 7, 8, 9, 10. This is the longest increasing subsequence. Now, this is a long increasing subsequence, that is clear. Why is it the longest? Can there be any other subsequence that are bigger than this subsequence which is increasing also? These are the kind of questions that one needs to handle. So, in other words, given a set of integers, we want to find an algorithm to finding the longest increasing subsequence. So, say we have been given a1 to an, where all the ai's are integers. Note that here integers is nothing special, it is just a example. You can take any numbers, even alphabets, anything where there is an ordering, because we are talking about increasing, decreasing and so on. So, there has to be an ordering among the symbols. So, we have a given a1 to ai n's and ai's are integer, and we want to output the longest increasing subsequence of a1 to an. You might find it very similar to other problems like longest common subsequence and so on, and if you are thinking of that in that direction, you are right. We will come back to it after some time. So, to start with, let us try our first attempt. The first attempt is the brute force search. What do we do here? We consider all the subsequences of a1 to an, all possible subsequences that can be there. Now, once we have selected a subsequence, we check if the subsequence is increasing, and if the subsequence is increasing, we keep it aside. At the end, we output the longest of such subsequence. Clearly, this will be the right output, because we would exhaustively search through all the subsequence, and we will be outputting the longest subsequence, which is increasing also. So, this approach is clearly an algorithm that will find it out. But recall, in our example that we had, if we had something like around 15 integers. Now, how many steps will be required to solve it using this brute force? It turns out the total number of possible subsequence is 2 to the power n, because I can pick any subsequence in that any of this element a1 to an can be picked or not be picked. So, under any such combination of can be picked and not be picked, you would get a subsequence. So, the total number of possible subsequence is 2 to the power n. For each of these subsequences, we will be taking, in the worst case, around n steps to check if it is increasing, and in that case the total runtime or the number of steps required is around order n to the power n. In our setting, in our example, if n was 15, we would have got 15 into 2 to the power 15, a quantity that is enormously large, something we cannot hope to handle. The question is that can we do better? Now, just in the earlier examples, the idea is to go for recursive algorithm. Now, again, as we had talked about earlier, in the case of recursive algorithm, defining the recursive subproblems is always the hard part. In this case, it is even more so. So, let us start with first looking at this example. Now, in this example, we want to draw a graph. How do we draw the graph? The idea is that if I have two numbers which are one is less than the other, say 1 is less than 7, then I will draw an edge here, maybe an directed edge, and I will keep on doing it. So, in other words, from 9, so it will take me some time to draw it. From 8 I will draw an edge to 9, I will draw an edge to 9, and I will also draw another edge to 10. Okay, I also have to draw an edge to 8. I also have to draw an edge to 8. So, in other words, it says that these are the numbers that are bigger than 8 after 8. Similarly, for 2, I will have to draw an edge to 5. I draw an edge to 7. I cannot draw an edge to 1, but I can draw an edge to 9. I can draw an edge to 8. I can draw an edge to 7. I can draw an edge to 2. I can draw an edge to 7, 6. Similarly, I keep on doing it. Okay. So, thus given this list of sequence of numbers, I would be completely making a directed acyclic graph, or what is known as the DAG. Note that all the edges are going from left to right, and we will not have any cycles, because we cannot have a cycle, because if you start from any point, say for example 2, you will only go left. So, you cannot come back to itself. So, it does not have a cycle, it is a directed graph. So, it is called a directed acyclic graph, and thus the name DAG. So, I have not been able to complete this whole graph, because it will take me quite some time, but this is the idea in general. So, you completely create this DAG. Just to understand how many steps is required to complete the DAG, it is around order n square, because I have to look at any two elements in this sequence and join it by an edge. Now, once I am done with it, let me try to define the recursive definition. So, let LIS I, or in other words longest increasing sequence I, be the longest increasing subsequence of A1 to AI, not A1 to AN, but A1 to AI. This is very similar to how we had defined in the last lecture also in various things. So, what is the base case? Clearly LIS of 0 is 0, because if the sequence itself has no letter or no symbol, then the length of the longest increasing sequence is also just 0. And here is the interesting part. What happens if I consider, say, the longest increasing sequence at I, say in this case say 8, okay, I mean this number 1, 2, 3, 4, 5, 6, 7. So, LIS 7. Now, this will basically say, so this has edges from coming from this, all the things which are smaller than itself, and it has come edge from 2. Now, the longest increasing subsequence at this LIS is either it must have stopped at any of these points. So, it must be longest increasing subsequence at 1 or longest increasing subsequence at 7 or so on, or it can be the longest increasing subsequence right at this point. So, in other words, I will have the longest increasing subsequence is at j will be 1 plus the maximum longest increasing subsequence of I j, where I j is an edge and longest increasing subsequence at I. So, in other words, let us try to see understand what is happening. So, here if I have calculated the longest increasing subsequence up to 7, up to this point, say in this case, say I know that longest increasing subsequence is 3, because I had a sequence 2, 5, 7. Now, that means that I can now add this edge, and since there is an edge from 7 to 8, so I can add this 8 into this longest increasing subsequence and get a longest increasing subsequence of length 3 plus 1, which is 4. So, 1 plus max of this set. This is not exactly correct. So, it is this, and you have to take also the maximum that ends at the one just below before it. In this case, maybe the longest increasing subsequence ended at 9 and 8 is not at all required. So, I also have to look at LIS j minus 1, you take max of these two objects. So, this will give us the recursive call to LIS or longest increasing subsequence at I. The idea is simple, let me just recall once again, is that either it uses the last bit, which is the LIS j, it either uses the ajth bit. In that case, you look at all the edges I j and look at the LIS I, and in that case you can add 1 to that object, or you do not use the LIS j. In this case, you just go down by 1, LIS j minus 1. So, this gives me the recursive algorithm, and we have this usual pseudo code. But interesting part is that what is the runtime of this algorithm? Note that we will be calling this LIS at various places. So, it will be T n times T n minus 1. In other words, T n will be of the something like n factorial, which is n to the power n. Not good at all compared to we had got by brute force method, but the idea is that this recursive algorithm can be quickly be used to obtain a dynamic programming algorithm, which can be better. So, let us take a small break now. After the break, we will look at the dynamic programming approach. Welcome back after the break. Before the break, we saw the recursive algorithm for solving the longest increasing subsequence, and we saw that its runtime was not very good, but we know that we can use this kind of technique to obtain a dynamic programming approach. So, how can we do it? Using dynamic programming. Just to quickly recap, dynamic programming is just like two other techniques of algorithms that we have seen, divide and conquer and greedy algorithm. And dynamic programming, the idea is to divide the problem into smaller sub problems. This is something we do also in the case of recursive algorithm, but then we will solve the sub problems and save it in a table, so that we do not have to recompute it again and again, and then we combine all the solutions to obtain a subproblems. So, in this case the idea is exactly same, where we do the same thing, and I will not go over all over again because we have done it so many times, but the idea is that when I am computing the LIS I, we can write it down on a table. So, let us just quickly go over it a little bit. So, LIS 1 means you have just looked at only one element, so is 8. In that case, the longest common subsequence is of course just 1, we know that. When we come to here, LIS 2 is either LIS 1, or if there is an edge coming into it, it is 1 plus the LIS of that object, but there is now edge coming to 2, there is no element here is smaller than 2. So, it will be just LIS of this one, which is 1. Similarly, for this one, say at this point it has one edge coming from 2, correct, because recall that in our the DAG that we have created, there is an edge from 2 to 5. Now, the LIS of this one is either the LIS of 1 less than that, which is in this case just 1, or if there is an edge coming inside, which is the edge coming from 2 to 5, it is the LIS of a 2 plus this object. So, in this case LIS at 2 is just 2 because it uses this one, and LIS of 5, that means I get here 2, and similarly for 3 I will get LIS of 5 plus 1, which is 3, and so on. So, I will keep on doing this kind of argument, and note that every time I do not have to go back too further down, because I do not have to recompute all of it, because it is already written here. But for every one, say for example, in this case when we land up in say 7, I have to look at all the edges, I have to go through this set to see which one do I have an edge, and therefore, for computing any one of them, I might have to scan over this whole set n times. So, in other words, this dynamic approach of course will give me the right answer, because I am doing nothing more than the recursive algorithm, but the algorithm will stop after the whole table is full. The algorithm has to make the DAG, making the DAG itself takes order n square steps. The table contains just n space, but each space takes order n steps, and the runtime is order n square, clearly much better than anywhere. The question is that can we do better than this? So, let me give you a different approach to solving this problem using dynamic programming only, but using a reduction to an earlier known problem. So, this is the case when we reduce it to the longest common subsequence. So, to quickly recap, given two sequences of symbols, if you want to determine the longest subsequence, that is the subsequence to both of them. So, this is called the longest common subsequence, and our goal is to output the longest common subsequence. We saw it in the last lecture that one can use dynamic programming and compute the longest common subsequence of two strings of length n and m in times order n m. I will now give you a very simple algorithm using this longest common subsequence algorithm to compute the longest increasing subsequence algorithm. Here is the algorithm. So, sort this string. So, I first sort the A1 to AN. Now, let the sorted string be B1 to Bn. So, things have been moved around here, I get B1 to Bn. I output the longest common subsequence between A1 to AN and B1 to Bn, and I claim that this is my answer. The longest common subsequence of A1 to AN, or any subsequence or common subsequence of A1 to AN and B1 to Bn, must be increasing, because it is a subsequence of B1 to Bn which is sorted. So, the output is at least an increasing subsequence of A1 to AN. And why is it longest? Because the longest subsequence of A1 to AN is also a subsequence of B1 to Bn, because B1 to Bn is a sorted thing, that subsequence will not be changed. So, in other words, the output is an increasing subsequence, and if there exists any larger increasing subsequence, then it is also a common subsequence of A1 to En and B1 to Bn. What is the runtime of the algorithm? The runtime of the algorithm is that to sort it we require order n log n steps, as we had seen earlier, and So, finding the longest common subsequence between these two strings, we take order n square steps. Thus, the runtime of longest increasing subsequence is order n square. To summarize, we can compute the dynamic programming the longest increasing subsequence in order n square. A quick recap of what we did till now. We had looked at the longest increasing subsequence. We saw that the brute force approach does not work very good. We did a recursive algorithm. The recursive algorithm also did not do very well, but we can easily convert the recursive algorithm into a dynamic programming algorithm, which was good. On the other hand, we can also reuse our earlier algorithm of longest common subsequence and obtain a very simple after the reduction algorithm for longest increasing subsequence. The last part of the reduction that we talked about is a very crucial part of the field of algorithms, where many times solving a problem all from scratch is not necessary. This is something we have seen in the case of graph algorithms a bit and we see it here. And in general, the idea is that if you get a problem to solve, it is sometimes easy to reduce it to a known problem and use the algorithm of that known problem. This is something that one needs to do a lot of exercise of, how to reduce one problem to another problem. Now that we have this algorithm for longest increasing subsequence, a natural question to ask is that, is this the best one can do? It turns out that yes, we can do it better, but this time not using any standard technique. So, till now we have talked about various techniques for solving algorithms. We have told that there is recursive algorithm, divide and conquer algorithm, greedy algorithm, dynamic programming approach and so on. But the most important thing to know about this algorithm lectures is that although there are various techniques that we can have in our hand, after all the goal of this algorithms is to solve a problem in a quick time, and sometimes not following any algorithm and coming up with a completely new technique is the only solution. Our whole of our research is basically based on exactly this kind of new techniques. So, now let me present you guys a very new technique, or not even technique, a new approach to solve this problem. One cannot call this one as a technique, because it is a very made for this particular problem approach. So, it turns out that this is also the optimal algorithm. I will not talk about why is it optimal. So, we have been given A1 to AN, and we will maintain an array of length n. At the round j, mean after we have seen, we will go over it round by round. Every round we will see one more symbol in A1 to AN. So, in the round j, I have seen A1 to AJ. At this point, this array will hold AI, the ith place will hold the least possible value of the last element of the increasing subsequence of length I in the sequence A1 to AJ. Where the round j, I have looked at A1 to AJ, AI should hold the least possible value of the last element in the increasing subsequence of length I. Maybe I should explain it more clearly using an example. At the round j, say I have seen up to 2. So, I have seen the red colored things 8, 2, 5, 7, 1, 9, 8, 7, 2. And let us try to understand what the values of this array should be. Values of the array 1 basically says that if I am looking at a increasing subsequence of length 1, what is the minimum that it can be? Of course, I can pick 8. 8 can be a increasing subsequence of length 1, but I can also pick up 1, and that 1 can be an increasing subsequence of length 1, and since this is the least, so I will put this one over here. So, now say 2. What are the increasing subsequences of length 2 in this thing that we have seen till now? So, of course, we can have say something like the 2 and 7 is one possibility. I can also say that okay, 8 and 9 is another increasing subsequence of length 2. But note that I am concerned about the last element of this increasing subsequences, in this case 7, in this case 9. and I want to pick the increasing subsequence of length 2 with the minimum last value. It turns out that I can have 1 and 2, and in that case the minimum increasing subsequence will be 2. So, I will store 2 over here. So, let us say 3. So, what is 3? I want to look at the increasing subsequence of length 3 and consider the minimum value. Again I can look at something like 2, 5, 8 is one such thing I can look at, but then I am considering about 8, that is the last one, and how low can I get that last one to be. It turns out that here if I look at 2, 5 and 7, this is the least I can hope for, and so 7 will be the least of the last one. So, I will put 7 here. I will need to look at a string of length 4, and a string of length 4 will be of the form 2, 5, 7 and 7, and again so that will give me 7 here. At this point what we are looking at the increasing subsequence of length 5, and since there is no increasing subsequence of length 5 available here, I will put them as infinity. Now, let us look at the next step. When we look at the next element, which is 8, this 8 we will be looking at the first element here, which is smaller than 8, or the last element here, which in this case is 4, and basically this says that I have a increasing subsequence of length 4 here, meaning which is this one 7 and 7, and it says that, see, I am smaller than this. So, I can add myself to it and get a increasing subsequence of length 5, and so I can update this value from infinity to 8. So, in other words, we will be able to keep on updating this array every time. The idea is that for every time we find the largest index I such that a I is less than or equal to j, and update a I plus 1 equals to a j. The runtime of the algorithm is simple. We have n rounds. Every round we have to find out the largest index which is smaller than the element we are looking for. For that we need to do a binary search which takes order n, order log n steps. So, in other words, the total runtime will become order n log n, better than order n square that we have. So, to summarize, we have a brute force algorithm that takes exponential time, dynamic algorithm takes order n square steps, reduction to longest common subsequence will take order n square steps, and a very clever algorithm will take order n log n steps, and that is the optimal. So, with this we come to the end of this lecture. We will talk about algorithms in general more in the next lecture. Thank you.